Now we're going to talk about a few issues related to digital image representation. That's section 2.4 of our textbook. We've seen that an image is basically represented as a matrix. And the way you index this matrix is the following. The origin is usually the top left corner of the image. That's the origin 0.0. And then you follow the row and column representation that we are all used to on matrix representation. So for instance, this pixel here is the pixel I, J is the pixel located at row I in column J. And the function related to this location is the intensity of that pixel. Well, can either represent it like this, but usually what you see is just a matrix. A few decisions that should be made with respect to the size of this matrix. You see that this is a matrix of m rows and n columns. So this is an m times n matrix. And we have to take into account the number L, that's the number of discrete intensity levels. That's the granularity of your quantization process. Usually there is no restriction with respect to m and n, only that they should be positive integers. And of course, the larger the size of the matrix, the more memory you're going to have to have in order to store the image. Digital storage and quantization hardware leads to the number L to be an integer of power of 2. Why power of 2? Because that's a binary image. Sorry, not a binary image, but that's an image represented by binary numbers. The only thing that I can represent in a computer is a binary number. So this is the size of this is the number L of discrete intensity levels will be 2 to the power of k. And the discrete levels for the intensity are equally spaced in the interval 0 to L minus 1. And a few important concepts. First one is the dynamic range. You're going to hear about noise and saturation forever if you haven't heard it before. It's basically, the dynamic range is basically the range of values spanned by the gray scale. It's represented as the ratio of the maximum measurable intensity, the top of our scale, to the minimum detectable intensity. The upper limit is saturation, right? So saturation is basically here a portion of the image that has a intensity that is greater than the maximum measurable intensity level. So this has no texture. You see, there's just a blob of very bright light. You see no features of this region. Let me put a pointer, maybe it's better. So you see no features here. At the other end of the scale, you have the lower limit, which when we see noise. So noise is basically things that cannot be, or some kinds of noise, this kind of dynamic range noise, are things that cannot be represented by the lowest limit of your dynamic range. Image contrast is the difference in intensity between the highest and lowest intensity level of an image. And another concept is the contrast ratio, with the ratio of luminance of the brightest color, usually white, to that of the darkest color, black, that the system is capable of producing. So if you hear that, oh, this camera has a high dynamic range, just means that it has a high contrast. It has a great value for the brightest color and a lowest value of the darkest color very far apart, meaning that you have a high dynamic range. You have a large amount of values that you can use to represent your image. Storage, there is a whole chapter on the book. It's chapter 8 of our digital image processing book about image compression and watermarking. which unfortunately I won't have time to talk about during this topic, but you can read it through. It's all based on calculating the storage and how you can generate algorithms to compress. And there's a lot of money on that. You know that Netflix is Netflix because of the compression algorithm. So in a very most fundamental sense, the number of bits to store a digital image is calculated by m times n. This is the size of the matrix times the intensity levels that you have to represent the image. Of course, if m is equal to n, you have a quadratic relation between the bits necessary to store the image and the size of the image. Right, and another observation that's it's actually a definition that people use all the time, the concept that people use all the time. We say that an image with 2 to the power of k intensity levels is a k-bit image. I'm sure you've seen something written like 8-bit image, 32-bit image. It's just represents the number of intensity levels, the size of your dynamic range. So an 8-bit image is just an image that has 256 intensity levels to represent. Why 256? Well, 2 to the power of 8, right? It's an 8-bit image. I think this slide is basically what's written here, right? It's just relating this storage with the quadratic of the size. So you see that there's a quadratic relation between the storage necessary. This is in megabytes. That's why this quadratic is kind of smoother to the size of the matrix that you have. Okay, so there are many ways of representing a matrix, right? It's not only this very boring way that you've learned on year 5, right? I don't know when you learned that, but I hope it was long ago. You can represent a matrix as a linear array, and that's a technique that is widely used in computer vision and image processing. What it is that you just transform this image, you get every number from here. Let me get a pen. And you linearize your matrix by doing the following. You get every number here and put on a linear array. So here in here and here in there. Let's do this properly. So each one is a cell, and so on and so forth until you get here. Once you get here, you store this. Let's suppose that this value here, x, is here. Once you get to x, the next number will be placed here, and so on and so forth. Getting here comes back, so you transform this matrix into a linear array. Why do we use that? Because some algorithms we can develop entirely. Actually, these are the way of optimizing this kind of algorithms is writing them as linear algebra equations. So you transform your whole image processing algorithm, your computer vision algorithm, into matrix operations. And some of these operations you need to take the complement of the matrix or to the linearization of the matrix, the inverse of the matrix. So all of these functions are very important to understand. Related to the concept of dynamic range is the spatial intensity resolution. This is a side product of the discretization of the image, as we've seen in a previous lecture. You can discretize it with a fine granularity, such as 930 dots per unit. That's dots per inch. DPI is dots per inch, or this is you can also use other units. We also use line pairs per unit. It's just the number of dots that I have per inch, number of dots in an image. Of course, if I have more dots, if I have a dense representation of this image, I'm going to have a very sharp image. If I have an image of low spatial intensity, like this one, I have it's a lighter image for in terms of storage, but you see gaps in the information here, right? So why do we need that? Because if we want to get this image and make it into a smaller image, shrink it in order to save space, I just get rid of a number of pixels here and transform one image that's 930 dpi to an image that's 150 dpi, 72 dpi. This is for saving storage, for saving storage, and also for doing manipulations. It's easier to do, it's faster to do a manipulation on a matrix of low spatial intensity if you don't care about details. In parallel to the spatial intensity, this is spatial intensity is the way you discretize your image on space. If you don't remember that, go back to the previous lecture. We have also intensity resolution. This is the number of intensity levels that I have that are available to represent an image. So for instance, this is a 256 level image, this one, which is pretty detailed. And this is an image with not a lot of resources as this one, but you see that given the number of details that I have in this image, changing from 256 to 128 didn't change much. But if you take, for instance, this image that is being constructed with 32 intensity levels only, we start seeing artifacts that are called false contours. So you see these contours here, they are not part of this of the original image, right? Of the specimen. That's a person here, right? It's not part of the person's brain. This is an artifact of the low intensity resolution. What's going on here is there is small variations in intensity. Let's say let's pick up this region here. Look at here. You see there is a small variation in intensity here. But if you don't have a very fine granularity, these tiny bits of this tiny variation from here is transformed into a greater difference between the intensity, the representation of intensity of this pixel here, than to this pixel in a more granular scale. And you can go crazy and keep changing, putting the image with the lower intensity levels. You're gonna find, especially this one, the false contours are quite apparent. So you see, right? Okay. This image interpolation is it's a basic process that you use in order to do the zooming of an image, shrinking and rotating. What it is that once you get, let's pick up this example here. I'll just erase it all. This example here, where this is for instance, a small image that's 72 dpi, 72 points per inch, and I want to zoom in, transform this image into a larger image. That's exactly what they've done here to obtain this image. You're gonna see that these pixels are now gonna be sparse. So let's see, let's suppose that we had a circle here, and this circle will be represented sparsely. That's what's going on. So what interpolation does is that it tries to reconstruct this line here with fewer information. So this guy here doesn't have a lot of information about that, but you can judge what would be the values to be included in these pixels here, given well, a number of methods of interpolation. One of them, the simplest one, you just assign to each new location, meaning each new pixel that I don't know the value of, I assign to each new pixel the intensity of its nearest neighbor in the original image. It's simple, but may cause distortion at straight edges, right? Where you don't have the nearest. Where the nearest is nothing at the edges of the image, and you have to guess the value of this pixel given this guy that doesn't exist, that falls into the vacuum of nothingness, right? Another better method would be to use bilinear interpolation. You use the 4 nearest neighbors to estimate the intensity of the given location. Let's go back to our example. Our example is here. I want to estimate the value of this pixel. So I go to the original image. This pixel would probably be located somewhere here. So I get the value of the 4 nearest pixels and do a sort of calculation to verify it could be the mean value, or it could be the median value. It could be a lot of there are many possibilities for doing that to interpolate the value, or by cubic interpolation that you use 16 nearest neighbors of a point. This is the result of reconstructing an image or zooming in an image of 72 dpi. It's zoomed to 930 dpi's. And this is being reconstructed by the nearest neighbor interpolation. And this is the same image reconstructed but using bilinear interpolation. You see that it has more information, it's smoother, but it's actually blurred, somehow blurred. And this is the same image but zoomed in with using bicubic interpolation. And that's it for this session. Next one, get prepared, get a cup of coffee, because next one is the most fundamental of our sections for lecture 2, which is a section about the fundamental mathematical tools. It's basically the stuff that we're going to be using throughout this course. I'll see you in a bit.